Hey guys, and welcome back to another video. This is the second video of the functions topic, or, well, the functions and graphs, trig functions and exponential functions topic, the second video. So I'm going to be dealing with quadratics, which I would say are the second easiest function to deal with, where lines involve degree 1, that is the highest power to which an x is raised is 1. Quadratics involve the highest degree as being a 2. So cool, let's get straight into it. So the first thing I'm going to be doing is looking at the sort of mathematical techniques that you'll be using to deal with quadratics in terms of factorizing quadratics and expanding quadratics. And that's really central if you're trying to move from different ways of writing quadratics, that is the general standard form or to the turning point form, to the root form. Factorizing and expanding is really, really important in that sense, and so that's what I'm going to be starting with. Then I'll be introducing those different ways of writing quadratics, the general or standard form, the turning point form, and then the root form, and I'll be looking at what each of those different ways of writing quadratics tell us about the quadratic function. After that, I'll be looking at how you can interconvert between those different ways of writing the quadratic function. I'll be introducing the quadratic formula and completing the square. The quadratic formula and completing the square do very similar things, but some of them might have advantages over the other for certain equations, for example, and I'll be looking at where those advantages might exist. I'll then have a look at, like we did with lines, converting between equations and graphs, how to determine the equation, the Cartesian equation, the Cartesian representation of a quadratic given an equation, or how to determine the equation of a quadratic given a Cartesian graphic representation of it. And that will take us to the end of it. I'll start now. Okay, so the first thing I want to mention is what I said in the introduction, and that's namely that quadratic equations are of degree 2. An example of a quadratic equation is the equation y equals ax squared plus bx plus c, which is referred to as the general or standard form of a quadratic, and this 2 is the highest power of x, so a quadratic is known to be of degree 2. One of the most important things or arithmetic that you can do with quadratics is you can either factorize them or you can expand them. And generally, if you're trying to solve quadratics, for example, what you generally do is you move from expanding from their expanded form to their factorized form. So an example of where we might expand a quadratic might be, let's have an example like y equals x squared plus 5x plus 6. And generally what we want to do in the case of quadratics is we want to find two numbers that sum to the coefficient of x and multiply to the constant in the equation. So we need to find two numbers that sum to this and multiply to this. And in this case, our two numbers would be 2 and 3. And this is something that comes with practice. It becomes easier and easier to see as time goes on. And now the next thing we want to do is we want to split up this coefficient as the sum of those two numbers. So we have that's equal to y equals x squared plus 2x plus 3x plus 6. And this is where we do our first factorization. These two numbers here share a common factor, and namely that common factor here is the x. We have a common factor x. And so we can factorize this according to x, and x times x equals x squared, plus 2 times x equals 2x. And then we can add, these share a common factor of 3, so we have a 3x plus 2. And as a result, we should have these two factors here. And the important thing is that between these first two numbers and these second two numbers, we always need to choose the highest common factor in order to ensure that these are the factors that we get at the end. And so what we do now is we can factorize by grouping. we have one bracket here, and the other bracket in the factorized form of the quadratic will be comprised of this and this here. And so as a result, our factorized form will be x plus 3 multiplied by x plus 2. And if we want to verify that this is equal to this, we can also expand it. And the way we expand is we use a crab claw method, or as you get more practice, this will basically come to you naturally. But you'll be multiplying this number first to get x squared plus 2x. And so you get x squared plus 2x. And then you get to 3 times x equals 3x, plus 3 times 2 is 6, plus 3x plus 6, which is equal to x squared plus 5x plus 6. Okay? All right. This can get a little bit more complex. In this case, what we've dealt with is a monic quadratic, in the case where the coefficient of our x squared is 1. We can also be dealing with non-monic quadratics in the case of, for example, y equals 2x squared plus 4x plus 2. Okay? And so in this case, what we want to do is we want to find something that, first of all, sums to this and multiplies to this number multiplied by this number. So we want to find something that, in fact, multiplies to 4 rather than 2. This is only the case for non-monic quadratics. And the reason why it's that is because in the case of monic quadratics, what's happening is you're multiplying 6 by 1, and so it doesn't actually matter. Okay, so we want to find two numbers that sum to 4 and multiply to 4, and those two numbers will be 2 and 2. And so we can write y equals 2x squared plus 4x plus 2 as y equals 2x squared plus 2x plus 2x plus 2. And factorizing, these two share a common factor of 2x, that's the highest common factor. 2x, x plus 1. These share a highest common factor of 2, so 2 multiplied by x plus 1. And we can factorize that by grouping to get 2x plus 2 multiplied by x plus 1. And in fact, we can simplify this even further because both these components share a common factor of 2. So this component can also be written as 2 multiplied by x plus 1, and then we have the x plus 1 from previously. Okay, so that's factorizing and expanding, and I would advise that you take a little bit more practice with some of the Sadler questions to kind of get a handle on that if you haven't looked at factorizing and expanding quadratics in previous years. Okay, so now that I've gone over factorization and expansion, I'll go over a couple of different ways we can write quadratics. So the first way we can write them is y equals ax squared plus bx plus c. So this is our first way. Our second way that I'll label is this one, y equals a x take h squared plus k, 3 y equals a x take p x take q, and these are the three different forms. And importantly, these different forms will have different associated names and tell us different things. So this is the first standard or general form. So standard slash general. The second is our turning point form. And the third is our root form. And something I will just take as given for now, but which I'll explore a little bit later as we go into the Cartesian representation of quadratics, is that a quadratic when graphed looks something like this. Actually, I'll give this example here. Okay? And so it'll have an associated x-intercept here, and it'll have an associated y-intercept here. And it'll have a turning point right here. And so based on the fact that this number 2 is labeled turning point form, you can already guess what information it kind of tells us about the graph, namely its turning point. And its turning point, more specifically, will be given by the point h, comma, k. That is this point here h and this point here k. And it's important that you note that this is a minus and this is a plus. So if you have, for example, in this case, as an example, maybe you have y equals x plus 2 squared, take 3, your turning point will be negative 2, comma, negative 3, because this can equally be written as x minus minus 2 squared plus 3. Okay? So that tells us the turning point. Now, the standard or general form will generally tell us the y-intercept, and the y-intercept will be equal to this. So it'll be 0, comma, c. And the reason why that's the case is because when we have our y-intercept, our x is equal to 0. Okay? So if x is equal to 0, that'll cancel this point out. That'll cancel this point out to 0 and 0. And so at x equals 0, y equals c. And finally, we have our root form. So at our roots, those are also known as our x-intercepts. And as you notice in this case, we have 2 x-intercepts. And so each of those x-intercepts will be represented by p and q. Okay? And so the important thing to note there is that at the x-intercepts, we have y equals 0. And in order for this to be 0, we need either that to be 0, that to be 0, or that to be 0, right? And this is known as the Null Factor Law. So it tells us if we've got a product of a bunch of different numbers, it tells us if we have a product of a bunch of different numbers, so a, b, c equals 0, that must imply that a equals 0, or b equals 0, or c equals 0, etc. Okay? So in this case, either a equals 0, x take p equals 0, or x take q equals 0. If a doesn't equal 0, which I assure you it wouldn't, because we need our x squared value, and if a equals 0, then it cancels out all our x squareds. We need this value to be equal to 0, or this value to be equal to 0 to satisfy the null factor equation. And so as a result, in order to yield that, we need x to be equal to p in this case here to satisfy this being equal to 0, or q to satisfy this being equal to 0. And that's why this minus p is really important here as well. Okay, and the minus q. All right. We will have a look at special cases with the roots. For example, you might have quadratics that only have one point of intersection with the x-axis, where you maybe have something like this, and your turning point in this case is your point of intersection. Or you could also have something like this, and here we have no solutions, no real solutions, I should say. It does have something called complex solutions, which is part of the Year 11 Specialist and Year 12 Mathematics Specialist course, but for now that's not something to worry about, and if you're only doing methods, definitely not something to worry about. Okay, and I'll have a look at these in more detail when we go over the graphic representation of quadratics more broadly. So with that, let's get to this Cartesian representation. So we'll get to the next slide. So if we're given a quadratic equation, we want to be able to convert to the graph. And similarly, if we're given the graph, we also want to be able to convert back to the equation, in the same way we did that with lines. So let's say we're given an equation y equals, in this case, maybe we should go over something else first. Let me think. Yeah, let's go over this here first. Let's go over solving quadratic equations first, actually. Yeah, let's do that. Okay, solving quadratic equations. All right, so when it comes to solving quadratic equations, something really important is the process of being able to factorize from expanded form. Okay, and when we're solving quadratic equations, generally we want to be using the null factor law, and we'll see how we'll be using the null factor law shortly. So let's say, for example, we have an equation like x squared plus 7x equals negative 12. Okay? What we generally want to do, the first step we want to do when we're solving a quadratic equation is to have one side of this equation be equal to 0. And the easiest way we can do that is by bringing the 12 over to the left-hand side, or adding 12 to both sides. So 7x plus 12 equals 0. And so now we've got our equal to 0, and we can use a null factor law. We can write this as a product, as we saw in the root form, of two different linear variables. So that is like an x minus p and an x minus q. And the way we can do that is by factorizing. So in the case here, we've got x squared plus 7x plus 12. We want to figure something out that adds to 7 and multiplies to 12. And so these two numbers will be 3 and 4. They want to add to 7. 3 plus 4 is 7, and 3 times 4 is 12. And so as a result, we can write that as x squared plus 3x plus 4x plus 12, or x times x plus 3 plus 4x plus 3 equals 0. And then we can write this as x plus 4, x plus 3 equals 0. And so now we know, using the null factor law, that either this has to equal 0 or this has to equal 0. A in this case equals 1, so we've got a 1 out the front here. And so x plus 4 equals 0 or x minus 3 equals 0. From this we know that x has to equal minus 4. And from this we know x has to equal minus 3. Okay? So x equals minus 4 or x equals minus 3. And this is the solution for the quadratic equation x squared plus 7x plus 12. Okay? Essentially, the solution is we're finding our roots, which is what I showed on that previous slide. Now, the thing is, you might have a little bit more difficulty with solving an equation, and that can come in the form of having these two numbers here not being easily identifiable. So, for example, maybe you've got something like x squared plus 5x, or sorry, I'll write that better, x squared plus 5x plus 5. And in this case, it's a little bit less clear what sums to 5 and what multiplies to 5 here. So in this case, it's a little bit more tricky than just looking at it and then identifying two sets of numbers, because in this case, that's pretty much impossible. So what we can do instead is we can use something called the quadratic formula, if it's not so clear. All right. And what the quadratic formula tells us is the x-intercepts. And more specifically, so in the case of trying to solve a quadratic, like here in the instance equals 0, what the quadratic formula will tell us are these values here. The x equals minus 4 and the x equals minus 3. Obviously, for this equation, those won't be the solutions. But what the quadratic formula is equal to is x equals minus b plus or minus root b squared, take 4ac, divided by 2a. And I remember the first time I learned about this, it seemed like it came out of nowhere, and I didn't know what the b's, a's, or c's meant at all. So, let me explain. We have our general solution here, y equals ax squared plus bx plus c. Okay? And so that's what these variables here relate to. So this b is your coefficient of x, this a is your coefficient of x squared, and the c is your coefficient of c. And as you deal with the quadratic formula more and more, an intuitive understanding. You'll develop a bit of an intuitive understanding of how it works as well. And so it does get easier to deal with. And at some point you will be able to memorize this. So what your b is equal to in this case is 5 from this b here. All right, so the b corresponds to the 5, the a corresponds to 1, and the c corresponds to 5. So here we've got minus 5 plus or minus b squared is 5 squared, so 25. Take 4 multiplied by 1 multiplied by 5. And so we have that divided by 2 times 1. And that'll be equal to minus 5 plus or minus root 25 take 20 divided by 2. So minus 5 plus or minus root 5 divided by 2. All right. And so as a result, our two solutions are x equals minus 5 minus root 5, all divided by 2, or x equals minus 5 plus root 5, all divided by 2. And so those are our two solutions for the quadratic formula. And so if we wanted to write that in the form of a equation, we would write that as x minus 5 minus root 5 on 2, and x minus 5 plus root 5 on 2, like that, equals 0. And I'll leave it up to you to kind of simplify that. You can put a minus out the front and simplify all of that as well. Okay, cool. But these are your two solutions. All right, so we've looked at the quadratic formula now. There is actually another way of dealing with this as well, and that is known as completing the square. And completing the square particularly helps in cases where your coefficient of x is an even number. In the case where it's an odd number, as in this case, it's a little bit trickier, and you'll see why in a second. So for completing the square, what we want to do is we want to write our equation in terms of a perfect square. And what a perfect square is it's a repeated linear factor twice. So an example of a perfect square is x plus 1 all squared. And this is written as, in this case, as x squared plus 2x plus 1. So essentially what a perfect square is where the two numbers that add to this and the two numbers that multiply to this are the same number. In this case, it's 1 and 1. And so as a result, you end up with something like this. And the way we can construct a perfect square in the case of x squared plus 5x plus 5 is as writing it as x squared plus 5x plus the two numbers that can multiply to 5. And in this case, those two numbers are 5 on 2 and 5 on 2. So 2.5 plus 2.5 equals 5. And so we add plus 5 on 2 squared. And now that we've added a random 5 on 2, we also need to subtract a 5 on 2 squared and then have our 5 hanging out the back. And so this section here can be written as x plus 5 on 2 all squared, or if we really want to, we can write it out as like your x squared plus 5 on 2x plus 5 on 2x plus 5 on 2 all squared, and then go through the process. Something that you'll find that gets a lot easier with time is that in the case of monic quadratics, these numbers that you identify generally end up going straight in here. So it's a 4 becomes a x plus 4, and then a 3 becomes an x plus 3, and that's just the process I'll adopt here. But if you want to factorize by grouping, that's also something you can do. So you have your x plus 5 on 2 all squared, and then you have your minus 5 on 2 squared plus 5 equals 0. And so you have your x plus 5 on 2 all squared, and then this becomes minus 25 on 4 plus 5 on 4 is 5 is 20 on 4. And so I can write this as x plus 5 on 2 all squared minus 5 on 4. Okay, I'll just rub this section out. I'll leave everything other than the quadratic formula itself and the solution, so we can see that it yields the same solution. Okay. Oh, let's take that back. Oh boy. I'll just leave that there then. Okay. So now we can write this as x plus 5 on 2 squared minus 5 on 4. And I can write 5 on 4 as a perfect square itself. That is a repeated linear factor. So I can write x plus 5 on 2 all squared minus root 5 squared on 2 squared equals 0. And now that we've got to this stage, we've reached something called the difference of perfect squares. Okay? And this is a case of a squared minus b squared, where you have two repeated linear factors, the difference of two repeated linear factors. And as you can see here, we've got one perfect square minus another perfect square. This is our a, and this is our b. Okay? So we have a squared minus b squared. And what the difference of perfect squares law says is that a squared minus b squared equals a plus b multiplied by a minus b. And if we are to write this out and expand it again, we can see that this actually holds. A times a is a squared, a times minus b is minus ab, b times a is plus b times a, minus b times b is minus b squared. And so the negative ba and the ba are the same, so these cancel out to 0. And you get a squared minus b squared just as expected. So we use this difference of perfect squares. Let's move this difference of perfect squares a little bit over. So we've got some more space. And so if we write this difference of perfect squares out, we get x plus 5 on 2 plus the root 5 on 2. And then the x plus, that should be a plus, x plus 5 on 2, and in this case, minus root 5 on 2. And that's equal to 0. Okay? And so as a result, what we get is minus of this whole thing, or minus of this whole thing. So either x equals minus 5 plus root 5 on 2, which is equivalent to minus 5 minus root 5 on 2, or x equals minus 5 minus root 5 on 2, which is equal to minus 5 plus root 5 on 2. And you can see that these two equations are the same as these. And so through both completing the square and using the quadratic formula, we're able to factorize quadratics that are less easily factorizable. Okay? Now, there are some cases where even the quadratic formula and the completing the square formula won't help us. And that's in the case where there are actually no x solutions. No real x solutions. Okay? So that was the case of this graph where we don't have any roots. And so I'll give one example of where that's the case. So we've looked at the quadratic formula, we've looked at completing the square, we've looked at solving quadratic equations, and there are plenty more examples of this in your Sadler book. But for now, let's take a look where even with all of these techniques, it's impossible to solve. Okay, so this kind of looks at this 1.2.7. And the role of the discriminant more particularly. So the example that I was going to give is y equals x squared plus 5x plus 10. And I want to figure out where this intersects with the axis. I want to solve where this intersects with the x-axis. That is, I want to solve x squared plus 5x plus 10 equals 0. Okay? And so if I'm trying to think of two numbers that multiply to 10 and add to 5 and multiply to 10, there are no two numbers that readily come to mind. Okay, so the next thing I want to do is I want to move on to my quadratic equation. And so if I'm using my quadratic, I have x equals minus b plus or minus root b squared take 4ac over 2a, where, remember, from our turning normal form, we have, I'll just highlight this bit here, y equals ax squared plus bx plus c. So my b is 5 minus 5 plus or minus the square root of b squared 25 take 4 times 1 times 10. And all of that divided by our 1. Okay? And so we have minus 5 plus or minus the square root of 25 minus 400 over 2, which is equal to minus 5 plus or minus the square root of minus 375 divided by 2. And so here we're taking the square root of a negative number, and so this does not exist. There are no solutions for x. Okay? And so if this value here, b squared minus 4ac, if this b squared minus 4ac is less than 0, then that's going to imply we have no solutions. That is, the graph will look something like this. Okay? So there's that. And this section here, the name for this is the discriminant. And that is a really important piece of terminology. It's also given the sign this triangle. So your triangle, your discriminant is equal to b squared minus 4ac. And if your discriminant is less than 0, that implies no solutions. And as we saw in the previous examples, if it's greater than 0, we have two solutions, like in that previous example. And if we have if it equals 0, this equals 0, that means it's minus b plus or minus 0, which means you only really have one solution, minus b divided by 2a. So here you have one solution. And this is a really central concept to solving quadratics. Okay? And even if you're trying to solve, for example, let's say, rather than you're trying to find where it equals 0, you're trying to find where a quadratic equals 2, and you bring the 2 over, you'll see that even this quadratic doesn't even intersect 2. X squared plus 5x plus 8 equals 0 also doesn't have a solution. So it's even above the point y equals 2. Okay? All right. Cool. So we've looked at solving quadratics. We've looked at the quadratic formula. We've looked at completing the square. We've looked at solving. We've looked at turning points. We've understood the role of the discriminant. We've looked at quadratically related variables, obviously. All right. So now I think it's time we move on to the graphic Cartesian representation. So we have, again, I'll draw attention to our general form, y equals ax squared plus bx plus c, and this tells us our y-intercept 0, c. We have our turning point form, y equals a x take h all squared plus k, where our turning point, so this is our y-intercept, and then our turning point here is h, k. This is our turning point. And then finally, 3, we have y equals a x take p multiplied by x take q. And this tells us our two roots, p, 0 and q, 0. Okay, so these are our really important points here. This is our standard or general form. This is our turning point form. And the final one is our root form or x-intercept form. All right. Now the first thing I want to look at as a standardized sort of way of representing things is I want to look at our y equals x squared. And so if I look at the graph and I consider different x values, okay, I have my y-axis here, my x-axis here, and let's say I'm plugging in a 0 here. 0 squared is equal to 0. And if I look at 1, 1 squared is equal to 1. So I have something here. Importantly, minus 1 is squared. Minus 1 squared is also equal to 1. And if we progress to 2, 2 squared is equal to 4. Let's make that a bit better. 3, 4. Okay, so at 2, we're up to 4. And at minus 2 squared is also 4. And so as a result, what we have is we have a Cartesian representation of y equals x squared. If we join up these points and we progress even further, we have a graph that is symmetric about the y-axis. Okay, and minus 3 will pass through y equals 9, x equals minus 3 that is, and x equals 3 will also pass through y equals 9. But for now, let's leave it simple like this. And so we can already say a couple of things about this graph. We can say, first of all, that it has one root. It has a root at 0, 0, the origin. It also has a turning point at 0, 0. So it's our turning point and our singular root. So we know, because it's got a singular root, we know that our discriminant will be equal to 0. We also know that we observe that it's symmetric about this y-axis. And another thing that we observe is that our y-intercept is also 0. And so our turning point, root, and y-intercept in the graph y equals x squared are all the same. And you can kind of see that based on these variables here. We have an x minus h, in this case the h is 0, and the k is also 0, so we have y equals x squared. We also have a 1 in front of here, and we have a c equals 0, there's no constant added, we can write that as plus 0. We have a 0p and a 0q, and so we have x times x, our a here obviously equals 1. And so that's all in this case. If we wanted to change our a value, and we have here, for example, 2x squared, if we observe what happens now, we have still our point 0, 0. If we plug in 1 though, we are now up at 2. So up here, and here for minus 1. And at 2 and minus 2, we are now at the point 4 times 2 is 8. So even higher up. And I won't label that on the y-axis mainly because I cannot be bothered. But you kind of get the deal here. That's a very poorly drawn quadratic. But you can also use the Desmos graphing calculator for a bit more of a machine-generated graph that looks a lot better than what I've just drawn. All right. So we've identified some key points there. Now let's look at a slightly more complex sort of graph. Let's look at, for example, one that has this sort of form here. So let's say we have a y equals 2 x take 1 squared plus 3. Okay, and what we can immediately see is that this graph here, this equation has this form here, and this form is the turning point form. So what this equation already tells us is the turning point of our graph, and we know our turning point in this case will be 1, 3. Okay, so if we look at our graph, we know that it'll be at the point 1, 3, and this will be up here. And importantly, our a value is positive, so just as in the case of a equals x squared, we have it going upwards. In the case of a negative 2, we would be going down like this. And the reason why that's the case, we can see just by plugging in values. If we have 1 here and we put a negative out the front, then 1 will correspond to 1 squared is 1, and negative 1 because of the minus. So that's why if our a coefficient is negative, we have a reflection like this. But in this case, we don't need to worry about that. And so we know we have a turning point at 3, 1. Another important point we need to know is the y-intercept. And the way we can do that is by expanding this equation. So we can write that as 2, expanding this out, we can write that as x minus 1 plus 3 in the long form, which we can write out as 2 x squared take 2x plus 1 plus 3. And this also is a process that you'll get really quick at, and you'll be able to expand x minus 1 squared just like that. And so now we want to expand that out even further. Take 4x plus 2 plus 3. So we get 2x squared, take 4x plus 5. And so this tells us our y-intercept now, and we know our y-intercept is 0, 5. And so I'll label that on my axis here as 5. So I have this point 0, 5. And so in terms of my x-intercepts, I can already see that based on the fact that this graph is going to be curving upwards, that I won't have any x-intercept, so I won't even bother with that. But I put it through here, and because my graph is symmetrical, I know one direction here goes up by 2, so one direction in the other direction will also go through 5. And so I know like this. And that'll be my graph. And similarly, I'll be able to deduce what my equation is based on this graph as well. I'll know that my equation looks something like this. I'll know it's y equals a x minus 3 squared plus 5. Plus 3, sorry. Oh, my goodness. X minus 1 squared plus 3, given that the turning point here is at 1, 3. And I know if I expand things out, I should get something like a x take 1, well, that's equal to x squared take 2x plus 1 plus 3, and I get a x squared take 2ax plus a plus 3. And because I know my y-intercept is equal to 5, I know that a plus 3 must equal 5, and therefore a equals 2. And so I get the equation y equals 2 x take 1 squared plus 3. Okay, cool. So that's the turning point form I'm given. So I've knocked that off. We've knocked this off. And now let's finally look at us given a quadratic equation with the root form. So I'll just finish rubbing this out, and let's consider an equation, for example, y equals 3x squared, a 3 outside of x take 1, x plus 2. Okay? And so the immediate thing that we know is this is the root form. We know that our roots will be p and q. In this case, our p is 1, and our q is -2. So we know we have 2 points at 1, 0 and -2, 0. And if we want to find our turning point form, what we do is we expand this out, and then we start completing the square, as a matter of fact. And so if we're expanding this out here, we have y equals 3, and then we can leave this as x squared take x, plus x take 2. All right. And this is me just doing this mentally. If you still need to use the steps, then use the steps. And so from this point, what we want to do, we expand that out. 3x squared plus 3x takes 6. And we can form a perfect square. And look at 3x squared plus x. And then in this case, I haven't chosen the best numbers here either. Yeah, I'll have to go with it anyway. So I've got 1, so 1/2 and 1/2 sum to that. So I do plus 1/2 all squared minus 1/2 all squared, close the bracket, minus 6. And so I can have 3x plus 1/2 all squared, and then I can take this minus 1/2 squared outside. This is 1/4, that is, so that's 1/4. And then multiplying by 3, I get 3/4. So it's minus 3/4 minus 6. And if you need a little bit more to process that maths, make sure you're expanding out those steps. But this video is going quite long as it is. So you have your 3x plus 1/2 squared minus 3/4 minus 6. And so you have 3x plus 1/2 squared. And then you have minus 3 minus 24 and 4 minus 27 and 4. And so you end up with a turning point of minus 1/2 and minus minus 27 on 4. And I should have chosen better numbers, but here we are. And so we know, first of all, because a is positive, that our graph will look something like this. Okay, we know that our turning point is at -1/2. So at this is -1, -2. We know it'll be at -1/2 and at -27 on 4, which is a little bit less than -6. So we'll just put this arbitrarily as -27 on 4. And so we know it's at -1/2, -27 on 4. We also know that we have a root at 1, 0 and 2, 0. If we look at this, we also see that we have a y-intercept at y equals -6. So I'll put that y equals -6 here. And so we can write out our quadratic just like this. All right, that is a lot that I've just covered there. And I've kind of looked at this as well. I've covered that point too. This is a lot that I've gone over in quite a brief amount of time, and I haven't necessarily used the best examples. So please, 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 if you have any questions, make sure to ask them. If you have any better examples that you might want me to look over, that'll be something I consider in the supplementary videos when I answer all of your questions regarding this course. But other than that, that is pretty much all of those points done. So in this example, we had a look at some examples of quadratically related variables. We looked at y and x. We looked at the graphs y equals x squared, y equals a x take b squared plus c, and y equals a times x take b times x take c. We saw that they had a parabolic nature. By parabolic nature, I mean they were symmetric like this, and they curved upwards like this, or they curved downwards like this as well. We saw that they had turning points at this point here. We saw that they had an axis of symmetry. That's something I actually didn't go over. An axis of symmetry in this case is the symmetry that they have here. And we saw that they had intercepts. We saw that they had y-intercepts in this case and x-intercepts, or in some cases they had no x-intercepts. The thing is, they will always have y-intercepts because x extends infinitely in either direction and they progress over to the sides. So wherever it is, if it's even here and you think it never will, you just keep following it through and eventually it'll intersect with the y-axis. All right, we have solved quadratic equations. We've used the quadratic formula. We've completed the square. We've done all of this. We've determined the equation of a quadratic given a graph. So given a turning point, a y-intercept, and another point, we'll be able to do that, as you'll see from some of the Sadler exercises. We're able to determine turning points. We're able to understand the role of the discriminant, and we looked at the features of the general quadratic y equals ax squared plus bx plus c. All right, cool. And that does us. And this should read the 14th of October. The next video will be releasing on, it should be releasing on Tuesday actually, so that's the 15th of October. But make sure that you comment if you have any questions or if I've missed anything, and that you subscribe so you don't miss any new videos. But that's quadratics done. I know that one was quite dense. And I might not have used the best examples because I was coming up with them on the spot, but so if you do have any questions, make sure you post those in the comment section.